Well done. Let's go. Okay, this is Calculus Integrals Part 2, day number 5 notes on rotational volumes. Let's get started. First of all, this is what we did last week, Friday, I believe, right? We talked about the comparison test. And all that the comparison test said was, if you want to know whether or not an ugly function, as you calculate the area underneath it, has a finite um, what's the right way to say it? Whether or not it converges or diverges, find a function that's a little bit bigger than it all the time and determine whether or not that converges. Okay, if it does, then it would force that lower function to also converge. Likewise, if you go the other way around and you have a function, again, you don't want to integrate. These two functions are not nice to integrate. If I can find a function that's smaller than said function and it diverges, then it forces the upper function to also diverge. This is something we did last week, so you can compare that with your notes from last week. I'm not going to do it again. All right, so let's get on to the good stuff. So what would a disk look like? Let's say a solid disk, not like a compact disk with the hole in the middle. What would a disk look like? What shape? Circle, right? So a disk, and I'm not going to look at it straight on. I'm going to look at it from an angle, right? Let's say I'm looking at it from an angle. I'm looking at a disk, right? Okay, some of you are like, what? I don't like that. Okay, there's a circle. There is it rotated a little bit to the side. What would the area of that shape be? Pi r squared. Okay, with r being our radius. Right, with r being our radius. Okay, so let's just humor me for a second. If I wanted to take, say, some function that looked like this and find the volume of that function rotated around the x-axis, wouldn't that circle be one small disk for mankind, yeah, and one large disk for calculus? Okay. I could find an infinite number of disks such that if I add up all those disks, that was really poorly drawn. Let me try that again. Okay, thank you very much for that. You get a bonus point. Okay. That was really poor. You can see this solid being formed, right, as it's revolved around the x-axis. Very poorly done, right? Very poorly done. But that's the point. I can calculate a bunch of different areas of circles off to infinity, and then I find the volume. So we're going to do that in a couple minutes. Now let's talk about the washer method for a moment. Those of you who do any sort of work with, any sort of construction, you know that a washer is a circle with a hole in it, right? So a washer would look like such. Some of you are like, donuts? Tomorrow we donuts? No, cookies tomorrow. Cookies. Okay, let's not debate disk versus washer. What would the formula for its area be? Pi r squared minus pi r squared. All right, I'm gonna do something a little bit better on this one. I'm gonna take this, I'm gonna duplicate it, and I'm gonna make it smaller. Oh, this is not gonna look good. I know. It doesn't look that bad. All right, here, I can make this look better. Okay? Let's call this the x-axis, right? And I want to take this function, right? This function right here minus this function right here, and I want to revolve it around the x-axis. So it's going to create this purple space. Very poorly drawn. But I'm going to revolve that solid around the x-axis. There will be a hole. That hole is going to be small on the very end over here, and it's going to get larger and then get smaller again. Okay. So let's move on. Let's talk disk method. So disk method is your friend. Disk method is easy because it doesn't require a whole lot of algebra, except in this case, right? Of course. What would be the radius? What would be the radius of this circle? No, it won't be 1. What is r? What is r? What is this distance right here? That distance is not 1. It's 1 in that case, but it's not always 1. Well, that's not at the peak. That's the max height. And how do we get the max height? F of x. Okay, so here, let's talk through it. Okay, I'm going to go from 0 to pi over 2. Okay, and I'm going to take pi. I want a circle, right? I want to take pi r squared. And in this case, we'll go dx. Now you're like, r and x, why are those both in there? Well, because r is not a common or constant value. R changes all the time. What is r? Radius, and radius is the height of the function, right? And what is the height of the function? At one point, it's 1. At another point, it's square root of 3 over 2. At another point, it's 1/2. So what is r? R is sine of x. Why is that denying me? This, r, is sine of x. So we're going to take the integral from 0 to pi over 2 of pi times sine squared x dx. Why? Because the radius at any given point is whatever the output of sine x is. Right? Now, I mean, it's not easy to integrate sine squared x, so we have to adapt it. Okay, so let's do this for just a moment. Would you agree that 1 minus 2 sine squared x equals cosine of 2x? Remember that identity? That's in your blue packet. Yep. Okay, so if I want to solve for sine squared x, because it's not easy to integrate sine squared x, right? I could change it into 1 minus cosine squared x, but I'm in the same dilemma again, because then I have cosine squared x. So what I do then is I just simplify and find what sine squared x is. Well, I would subtract 1 and divide by negative 2. So that would be cosine 2x. Of course, this would be a black pen on some dark color, right? And that's going to deny me. That's cool. Minus 1, right? So I subtract 1, and then divide by negative 2. So sine squared x equals negative cosine 2x plus 1 over 2. Okay. Whew. Oh, that was all just to get that thing, right? Cool. I wanted to show you the math behind it just so you're aware. Okay, so let's integrate this. What can I do with pi immediately? Yeah, pull it out of there. Bring it to the outside, 0 to pi over 2 of this thing that we now have, which I'm going to call 1/2 minus 1/2 cosine 2x. That'll be much easier to integrate. Easier, right? Okay, so suggestion here, if I were you, I'd split this up into two separate integrals. So pi over 2, 0, this would be 1/2 dx minus the integral. I'm going to bring that 1/2 out. Cosine of 2x dx. What did I forget? I did forget something. This pi has to be distributed to everything. All right, I'd like you to take a moment with a neighbor, integrate that. Go. All right, let's see what we get here. So I integrate 1 over 2 dx to be 1/2 x minus 1/2 times the integral of cosine 2x dx, which would be 1/2 sine 2x. Plugging in pi over 2, let's evaluate down here. This will be pi times, that would be pi over 4 minus, what's the sine of pi? 0. So that'd be minus 1/4 of 0. Oops. And then minus 0 over here. So it looks like I have pi times pi over 4, which would equal pi squared over 4 units squared. Folks at home, I made a mistake. That should be units cubed, R. Okay. So what would big R be here? Big R is going to be the square root of x, and little r will be x squared. Okay, so I'm going to plug those in. Let's take a moment here to get this lined up. I don't have a whole lot of time, so I'm going to pause it. All right, so we've got big R squared. We said big R was square root of x, little r was x squared. Let's integrate this. Well, what is square root of x squared? X and x to the 4th. Wow, this one's actually pretty nice. Okay, let's integrate. 0 to 1, that should be, whoops, I don't want an integral when I'm about to integrate. So that'd be 1/2 x squared minus 1/5 x to the 5th. And we don't need plus c because this is a definite integral from 0 to 1. Okay, let's do some math, right? Let's take pi. What's going to happen if I plug 0 in for those? I'm going to get 0. So if I take 1/2 of 1 squared minus 1/5 of 1 squared, and then I subtract 0 from that. Well, 1/2 of 1 is 1/2, so it's going to be pi times 1/2 minus 1/5. Of course, fractions, thank you. So let's put that in tenths. That'd be 5/10 minus 2/10. So it looks like my volume of revolution here will be 3 pi over 10 units cubed. Okay. Children on the web, kind of creepy, but that should be a 1 and that should be squared, right? Yep. All right, one more time for you creepy kids on the web. This should be a 5. It should be a 5, but it doesn't change our answer, right? I got lucky there. Didn't change my answer. Now, if that was a 1/2 in there, then that would have been a problem. Instead of 1/4, we would have gotten 1/32, and then the whole problem changes. Okay. Think for part C. Could I just shift this whole space here? If I'm revolving it around this line right here, wouldn't that be the same as revolving this function around the x-axis? Right? So just take your functions and subtract what from them? E. Just subtract them down. Okay, so let's just talk some logistics there for a moment.